We're now in Physical Chemistry, Chapter 8, Section 4. We're going to talk about critical point calculations. Now remember, on the phase diagram, a tie line is a horizontal line, in this case pressure versus molar volume. So on that diagram, the tie line, we're going to be looking at where the vapor is condensing. Now with higher temperature, the tie line is going to get narrower. There's going to be a point where the tie line actually disappears. This is called the critical point. Now an inflection point is where both the derivative and the second derivative are equal to 0. Hopefully you learned that in calculus. To liquefy a gas, of course, we're going to need to be below the critical point. Now critical data for an equation of state. At the critical point, the polynomial has 3 real roots equal to each other. Below the critical point, the polynomial has 3 real roots that are different from each other. Above the critical point, the polynomial has no real roots. Now the critical temperature, remember, is roughly equal to 1.6 times the temperature of the normal boiling point. And the molar volume at the critical point is roughly equal to 2.7 times the molar volume at the normal boiling point. Now the equation of state, for the van der Waals equation of state, solved for pressure, we get pressure is equal to the gas constant R times temperature divided by the molar volume minus the correction term B minus the correction term A over molar volume squared. Now we want to take the derivative of that with respect to molar volume. So we get the derivative of pressure with respect to molar volume is equal to minus the gas constant R times temperature divided by the quantity of molar volume minus the correction term B squared plus 2 times the correction term A over molar volume cubed. We're going to call that equation 1 for future reference. And remember, at the critical point, that's going to be equal to 0. Now we're going to take the derivative of equation 1 with respect to molar volume. So we get the second derivative of pressure with respect to molar volume is equal to 2 times the gas constant R times T divided by the quantity molar volume minus B cubed minus 6 times the correction term A over molar volume to the 4th. We'll call this equation 2. And we're going to say this is equal to 0, 2. So we're like an inflection point. Now we're going to use equation 1 and equation 2 to solve for the values of those constants. So we get the pressure at the critical point is equal to R times the temperature at the critical point divided by the molar volume at the critical point minus B minus A over the molar volume at the critical point squared. Now we're going to divide equation 1 by equation 2. Now you could argue we're technically dividing by 0 at that point, but I'm not really sure why we can get away with that. But anyway, we'd have the molar volume at the critical point minus the correction term B divided by 2, and that's going to equal to the molar volume at the critical point divided by 3. So we end up with the molar volume at the critical point is equal to 3 times B. We'll call this equation 3 for future reference. Now we're going to get R times the critical temperature is equal to the molar volume minus C, or minus the correction term B squared equals 2A over molar volume cubed at the critical point, obviously. So we get R times the temperature at the critical point divided by 4 times B squared equals 2A over 27B cubed. So we solve for the molar volume at the critical point and we get 3B. So then we end up with the temperature at the critical point is 8A over 27RB. The pressure at the critical point is A over 27B squared. Or what's interesting, we can even solve for R and say, okay, R is equal to 8 times the pressure at the critical point times the molar volume of the critical point divided by 3 times the temperature of the critical point. Now Z, remember the compressibility factor, 3-line equal sign means defined as, or always equal to. So we're going to say the compressibility at the critical point is equal to the pressure at the critical point times the molar volume at the critical point divided by the gas constant R times the temperature at the critical point. And then substituting what we had up there, so we get A over 27B squared times 3b divided by r times 8a over 27 rb. That simplifies just to 3/8, or 0.375. Now remember though, for an ideal gas, Z is equal to 1. So solving for A, we get 27 R squared Tc squared, remember Tc is the temperature of the critical point, divided by 64 times the pressure of the critical point. And then the correction factor B is equal to R times the temperature of the critical point, divided by 8 times the pressure of the critical point. We could also say the molar volume of the critical point is equal to 3 times B.